NSGA could achieve some popularity, but it has got a few drawbacks. Now, to overcome these particular drawbacks, the concept of this NSGA 2 came. Now, in NSGA 2 actually what we do is the concept of sharing function approach, that is replaced by the crowding distance approach. Now, let us try to explain what do you mean by this crowding distance approach. Now, what we do? So, this crowding distance approach we use in place of sharing function approach to maintain the diversity in the population. Now, here let me take one example. Supposing that I am just going to solve the minimization problem involving two objectives f 1 and f 2, and supposing that this is the front one solution or the rank 1 solutions we have got. So, these are all rank 1 solution. Now, I will have to find out the solution for the mating pool. Now, here what we do is, supposing that I am just going to concentrate on a particular solution, the ith solution, and I want to find out what should be the crowding distance value corresponding to this particular the ith solution. Now, what we do is, so with respect to this I 1, with respect to this point I, so whatever is lying towards my right, that is I plus 1, and whatever is lying towards my left, that is I minus 1. So, these 2 points are considered. So, what I do is we try to form one cuboid. So, this is actually the cuboid surrounding this particular the point I, and we try to find out the side length of this particular cuboid, or we try to find out the perimeter of this particular the cuboid. And actually what we do is the crowding distance value for the ith solution is nothing but the sum of the side lengths of this particular the cuboid, and by following the same principle we try to calculate the crowding distance value for each of these particular the points, and then we do the proportionate selection based on the concept of this crowding distance value. Now, let us see how to implement. So, this particular the concept. Now, if I consider the points which are too far, the crowding distance value will be more for the points which are too far, and the points which are very close to each other, the crowding distance value will be less. That means, the crowding distance value will be less for more crowded solution. Now, if I just go back to the situation, so this particular situation let me concentrate. Now, here I am just going to consider there are only 5 solutions here on this rank 1. Now, the crowding distance value for this particular the point 1. So, that will be more, because if I want to just construct one cuboid. So, this is actually the cuboid, and this will go towards infinity. So, the crowding distance value for this particular point 1 will have very high value compared to this particular point 4. Now, if this for this particular 4 we have got this particular cuboid something like this, whose crowding distance value will be less. Now, this particular example I will take after some time, but before that let me try to concept on this particular the idea. The crowding distance value of ith solution lying on the front is the side length of the cuboid, which I have already discussed, and the crowding distance value will be less for more crowded solution, and for the end points the crowding distance value will be very high. So, the solutions having more crowding distance values will be preferred in the reproduction scheme to form the mating pool. And let me try to summarize whatever I told. Supposing that I have got say 13 points on rank 1. So, for each of the 13 points we try to find out the crowding distance values. Now, the points which are too far or the end points, the crowding distance value will have high value, and the points which are very close to each other, the crowding distance value will be less. Now, during this reproduction, the proportionate selection, if I give more preference to the solution which are lying on the side of this particular front, that means which are too far, there is a possibility there will be multiple copies of these particular points in the mating pool. And if I can ensure a large number of endpoints in this particular the mating pool, there is a possibility that the diversity of this particular population will be maintained. Now, this is the way actually we maintain this particular the diversity. Now, if I compare the concept of this particular crowding distance with that of the sharing function, now here the computational complexity will be much less compared to that of this concept of the sharing function. So, using this concept of your the crowding distance, this algorithm will be much faster. Now, to explain the working principle of this particular crowding distance, let me solve one numerical example. Now, this is a very simple example, and once again the problem is I am just going to minimize the two objectives f1 and f2, and supposing that this is the rank 1 solutions, this is the rank 1 solution, and here I have got only 5 solutions like 1, 2, 3, 4 and 5, and I have shown here the coordinates also. Now, if I want to find out what should be the cuboid corresponding to a particular solution, say solution 4. Now, surrounding the solution 4, the cuboid will be something like this. So, this is the cuboid, because here I have got solution 5, solution 3 here, and so this particular solution 4 will be surrounded by this particular the cuboid. And once you have got this particular cuboid, so very easily I can find out the side length, and we sum all the side length values. So, I will be getting the crowding distance value for this particular the 0.4. Similarly, if I want to find out the crowding distance value for this particular the crowding distance value for this particular 0.5. So, what I do is we try to find out whatever is lying towards the left of this particular 0.5, that is nothing but 0.4, and towards the right. So, there is nothing. So, we can assume that there is a point in infinity. So, the crowding distance value if I want to calculate, so I will have to consider so this type of actually the cuboid, and here actually there is no end because this is moving towards the infinity. That means, the side length values for this particular cuboid, the sum of the side length value will be very high, and let me assume a very high value 1000, 2000 something like that. Okay. Now, similarly following the same principle I can find out the crowding distance value for 0.1. Once again it will have a very high value, because this side the next point it is assumed that it is in infinity. So, it will have a very high value for the crowding distance. Then if I concentrate on 0.2, so I will have to find out the crowding distance value by considering this particular the cuboid. So, following this I can find out the crowding distance values for each of these particular the 5 points. Now, whatever I discussed, the same thing actually I have put it here. Now, for the 0.1, the crowding distance value will be very high, and let me consider it is infinite, it will have infinite value. Let me consider this is 1000 for simplicity. Okay. Now, perimeter of cuboid surrounding 0.2, surrounding 0.2 the perimeter, if we calculate this will become equal to 14 unit. Similarly, corresponding to cuboid, surrounding point 3. So, this is point 3. So, this particular cuboid and its perimeter is 8 unit. Similarly, the perimeter of cuboid surrounding point 4, this will become equal to 14 units, and the perimeter of cuboid surrounding point 5 will have very high value, okay, and let me assume that this is once again equal to 1000. So, these are all actually the crowding distance values, and as I told, the points which are having the more crowding distance values like 0.1 and 0.5. So, if we give more preference to those points in the mating pool during the proportionate selection, there is a possibility there will be more copies of 0.1 and 0.5 in the mating pool. That means, so this particular part and these particular points will not be lost from the population, and there is a possibility that I will be able to maintain the whole stretch of this particular the Pareto optimal front of solution, and there is no chance that a part of this particular Pareto optimal front will be lost, and we will be able to maintain actually the diversity of this particular solution or the stretch of the Pareto optimal front of solution. That means, we will be getting more options, more number of feasible optimal solutions will be getting. So, this is the way actually the concept of the crowding distance works just to maintain the diversity in this particular the population. Now, if I compare the computational complexity of this particular crowding distance calculation and that of sharing function calculation, it is obvious that this particular calculation of crowding distance values will be much faster compared to that of sharing function value, and that is why this particular algorithm will become faster compared to your the algorithm using the sharing function value. This is the concept of NSGA 2, and NSGA 2 is expected to be faster compared to this particular NSGA. And moreover, there is another thing which was missing in NSGA that has been incorporated here, that is the principle of elitism. So, in NSGA 2, the principle of this elitism has been used, and moreover, it has been made faster compared to NSGA, and that is why actually NSGA 2 become more popular compared to NSGA. And nowadays, this NSGA 2 is in use, many people have used, and it has been further modified also. Now, the advantages of NSGA 2, I have already mentioned that it is computationally faster than NSGA, and the principle of elitism has been used in this particular your NSGA 2. Now, using this NSGA 2, there is a possibility that we will be able to find out the Pareto front of solutions. Now, actually if you see the literature, there are a few other algorithms just to tackle this multi objective optimization problems, particularly the problem having either 2 or 3 objectives. For example, say we have got the algorithms like multi objective particle swarm optimization, that is called MOPSO. Then we have got multi objective simulated annealing, MOSA. We have got SPA algorithm, we have got PAES algorithm, and there are some other algorithms. So, this particular literature is huge, but the basic principle which I have already discussed. So, those principles only with little bit of modifications have been used to design and develop the tool for multi objective optimization. So, as I told, there are a large number of algorithms available to solve the problem involving either 2 or 3 objectives. There is of course a chance of further improvement of these particular the algorithms. Thank you.